Okay. Kieran, what are you coloring in? Thank you, Daniel. Let us talk a little bit about stars. Quasars, supernovas. So, we're going to start with the simplest star that we all know of, the sun. No, we don't have an actual picture of the sun from that close. It's impossible. So, I don't know why I put this line in here. We're going to ignore that. So our sun, it's called a yellow dwarf. A yellow dwarf star. Caleb, if you've got comments, Dad, you need to put your hand up.
I don't know how to spell this.
Matt, you want me to write it a little bigger? I will write it a little bigger. Here. Do you need dwarf spelled a little bigger? A yellow dwarf, like that. So, how a star works, folks, is it's got elements in it. Kieran, Daniel. Usually tons, but it's usually burning one specific type. Now, different ones burn different things. A yellow dwarf star is burning mostly hydrogen, which is like the most, nope, just hydrogen. Hydrogen peroxide is what you get when you mix hydrogen and other stuff. This is just pure hydrogen burning at the center of this star. Caleb, you couldn't get within 1,000 kilometers of it, right? It's an O. Hydrogen. Sorry, Maddie. So these are also called main sequence, which just means that they're the usual type of star. So like it's a star that's grown up, it's not really old, it's not really young, it's just doing its own thing. Oh, sorry, that's a Q. So I'll write this a little neater. That's better. That's a little better. So like I said, it's middle-aged. So stars like this are like our sun, a star like Alpha Centauri, which is the next closest star to us. And there's another one called Kepler 22, which is also like ours. Huh? Well, that's the star that they were going to in Lost in Space, is Alpha Centauri.
Oh, they got Lost in Space?
Yes, on the way to Alpha Centauri.
A movie?
It's a show on Netflix. Quite good. You guys could watch it. Yeah. Maddie, can you put the coloring away, please? It's going to be distracting. Okay, everybody good on our star? Caleb says no. Caleb, what else do you need to know about our star? You're good? Okay. So let's talk about the next type. So, next up, folks, is an orange dwarf. So these burn slower than yellow dwarfs. So it's a little bit older. Okay? These are cooler burning gases. So hydrogen tends to burn hotter. And other things like helium or nitrogen and all these other gases and things that stars are burning at the very middle and fusing together. Oh, we should take Whisper down. Much thanks, Daniel. They aren't burning as hot, so that way when we look at a star, it's not as yellow, right? It's not as bright. It's not burning the same things. It doesn't burn them as hot. Quinn. Yes, which creates a lot of heat. Technically not. But the term we use, Quinn, is burning. It's burning those elements, okay? Technically. Remember this week we're drawing Shrek?
Oh, yeah.
Okay, everybody give me a thumbs up. Are you ready to move on to the next page? Thumbs up if you're ready to move on to the next page. Caleb, what does that mean? Thank you. Next up is a red dwarf. So this is very slow burning. So compared to yellow, oh no, compared to yellow, they are very cold. So it's still hot, you still couldn't get close to it, but in comparison to a yellow star, this one's cold in terms of stars. It's still many millions of degrees in terms of how hot it is, but compared, as in the coldest, it's gonna be the next one on the list. Brown. Blue is actually hotter. Quinn first, and then Caleb. Quinn.
Not like our stars. Red dwarfs are actually more violent than our stars.
They're not, Quinn. They're not actually. Red means it's not burning as hot.
But it's basically, because it's not burning that much fuel, it flings out a lot of things.
Kind of. Not really. It's cooler. It's not doing as much. It's not as active. There's less fusion going on. It's more just kind of quiet. It's like if you put your car into 5th gear and you're gunning the gas, that's what a yellow star is like. If you put your car into neutral, it's just kind of sitting there and you're just sitting in your car and the engine's running, that's what a red dwarf star is like. It's just kind of sitting.
But because of the, for some reason...
Quinn, this sounds like a conversation you and me should have personally and not in front for the whole class, okay? Deal? Thank you. Caleb, you had a question.
145.
Hold on, I've got like 3 people talking and Caleb was the only one I asked for an answer. What do you mean? It wouldn't look like much. It would be so bright you wouldn't be able to see anything.
Yeah, this is you'd be very dead.
Kyler.
If that red dwarf is colder and way slower burning, does that mean you can get way closer to it?
You could get a bit closer, like maybe another 1,000 kilometers, but still nothing we make could get close enough to like make a difference. It wouldn't be a noticeable difference. So these ones live incredibly long. I'm talking trillions of years.
What?
These stars were around, like there were red dwarf stars around at the very instant of the universe starting.
The Big Bang Theory.
Like possibly even like according to the things they've done on the studies of the light coming into our telescopes versus the length of time for other stars and when they think the Big Bang happened, according to the math they've done, some red dwarfs technically have been around for longer than when we thought the Big Bang was. It's wild how old these stars are.
Okay.
Quinn, you have another question.
So my question is asking, can you please like raise up the size of trillion?
You want me to make trillions bigger? Yeah. That better? Quinn, we've got room up front. You could come up front. Okay. Hi. Kieran. Shh. We'll have some time after to discuss all of our fun, cool space thoughts. We just gotta get through this, okay? We all good for here? Yes, yes. Thumbs up if you're good for this page. Sweet. Next one. The brown dwarf. These don't. Black hole doesn't actually look like anything, so we'll get there. So they don't burn hydrogen. These are usually burning really weird gases. I don't know them off by heart. No, again, still too hot for us to get close to, Caleb. There is no such thing as a star that you could go up and walk around on. That doesn't exist. So here's the thing. So this is the same size as a red dwarf, but it's got more stuff. So there's more kind of gunk packed around it. So these will eventually turn back into things called nebulas, which are big giant clouds of gas. So it'll just eventually stop burning and all the gas just kind of like spreads back out again.
And then it'll...
Fun fact, Jupiter is like, if you took Jupiter and times it by maybe 3 more times in terms of the amount of gas that's in it, it could be another star. It's almost big enough to be another brown dwarf star.
Seriously?
I'm serious. Jupiter is almost big enough to be a star all by itself.
What if we just like took Saturn or whatever and just...
Smush them together, then possibly, yes, it could be a star.
But then they got 2 like...
Because for something to be a star, right, that inside core... Kieran, focus up. On a planet, the core of it isn't burning. Caleb, focus up. Caleb. But on a star, the inside has to be fusion happening. And the only way fusion happens if there's enough stuff pushing on the inside. So if Jupiter just currently doesn't have enough stuff pushing on its core to light things up inside. But if it just needs a little bit more, it could. Which would be bad, because the gravity of the whole solar system would be thrown way off. We'd have planets like being flung out all over the place. Yeah, it would just like, because then we'd have two orbits going on. It would be, there would be planets that would be being pulled between Earth's gravity and Jupiter's gravity. It's a mess. It would be an absolute mess. Quinn. Yes. Not. That's something we can talk about. That's more of a science fiction thing. There are ones with 2 stars. We don't know much about how they work. Are we all good on brown dwarfs? Everyone's good? Sweet. Let's talk about some of my favorites. These are blue giants. So these are young stars. These are young stars. These are just babies. These are only babies. These are just little babies. Oh, they're still much bigger than a yellow dwarf star, because these have just sucked in a bunch of material. They haven't had the chance to kind of burn through a bunch of it yet, so they are just these intense infernos. So these are the biggest and the hottest stars that exist in the universe, okay? So these are between 7,300 to 200,000 degrees Celsius.
That's hot.
That's really hot.
That's hot.
Yeah, I was about to say that.
That's hot.
That's a very hot.
It's really hot.
That's almost hot enough.
7,300 to 200.
Wait, what?
That's almost as hot as my uncle's cooking.
I feel like a blue giant star is going to be slightly hotter than your uncle's cooking.
Just slightly.
This chicken won't stand red, Jack.
Kieran, focus up. So, since these stars are so volatile and they're so full of like gas and they're constantly burning so hot, then they stop burning. They don't just like sputter out like a brown dwarf, right? They don't just go poof. These, who can tell me what happens when you have a really hot, really big star? Joseph, what happens?
Supernova.
They will cause a supernova.
Would we feel that?
No.
We would see it.
Does it take?
Well, here's the thing. Most blue giant stars are so far away that the supernova would happen, and maybe 15 years down the road, we'll be like, oh, look, that star doesn't exist. Well, it didn't exist 15 years ago.
These are P and E.
Oh, I'll make it bigger, Quinn. Sorry, bud.
Where?
That's cool.
Supernova.
Exactly. So what happens with a supernova, I'll draw it for you guys.
Sounds like candy corn.
So you take, here's your star. Here's the stuff all going inside, and then everything inside, it runs out of stuff. So there gets to be this like hole happens in the middle of the supernova. And then all the other stuff on the outside starts really rapidly going zoop, 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 into the space that was just made until it all gets too close and they kind of collide, and then you get and that's what we're gonna get to if there's even more material and it isn't all able to blow back out again. That's when you get
White. Oh, it's
nope. That's when you get a black hole.
oh.
Shh.
But it's really small.
Or, like Joseph said, or you get a thing called a neutron star,
There we go, neutron star. No,
which is where all the stuff just sucks in and it turns into this really, really dense, like, and when I say dense, like all the stuff that was in an enormous star is now packed super tightly into a really tiny star. Shh. Quinn,
Joseph was talking about a white dwarf.
white dwarf, neutron star.
Neutron star.
They're about the same, buddy. It's generally the same thing. It's a star that kind of ran out of stuff to burn and got sucked into a smaller version of itself.
Yeah, but it's very
Black
thin.
holes are scary.
Black holes are utterly terrifying.
You never want to get caught in one of those.
We can do a lecture on black holes. It's a big physics thing, so we'll have to talk about some chemistry first, but
What? What is that?
Joseph, not super appropriate, man. Not at all.
It's not gonna be friendly.
Okay, everybody good on blue giants? Thumbs up. Okay, Quinn, I'll give you a minute. Everybody else good on blue giants? Yes? Yes? Good? Okay.
Boom.
Mr. Worthington, you good on blue giants?
Black,
Sweet.
black holes scale me. Because you don't know what happened.
We good? Quinn?
What's happening to the physical world?
Caleb? No, I don't mean to offend. Your foot on your desk is distracting me. Thank you.
I'll do this then.
Good. Next up. It's your red giant.
What giant?
So, these are super late in their life. Red giants are old stars. Real old stars. So like our sun in a couple of billion years will probably turn into a red giant. So it stops burning and it starts expanding in size because there's not as much energy holding everything together, and it gets bigger and bigger. So these will eventually become brown dwarfs.
Can you go inside of it? No.
Caleb, stop asking the question. You know the answer. You can't go inside any of these, buddy. Or you'll become a like white dwarf or a black dwarf. A black dwarf is just a white dwarf that doesn't burn as much anymore. A black dwarf is basically just a dead bunch of gas that's still spitting.
Lame.
It's not as exciting.
So cool.
Kieran, the only person to make an issue out of that is you, buddy. So they kind of sputter out. They get enormous. So when our sun turns into a red giant, it will expand, like the Earth will be encompassed inside of it. It will grow that large.
So, well,
If human beings are still around, yes, we would get swallowed by the star, but we'd be dead long before it ever swallowed us up because we couldn't be that close to the surface of it without dying.
eventually we'll die.
Eventually, the Earth will not be a thing. Yes.
Like a couple billion years.
Couple of billion years. Again, that's so far in the future we can't even consider.
I finished another color. I keep spelling black.
Questions about red giants.
Like that's a brown black right there.
It's okay, Kier. My R has been a little messy, so I don't blame you.
Why did they say black?
It's all good. I hear you, buddy. I hear you. Quinn, you good? Sweet. Everybody else good? Let's go. We are almost through here. So let's talk about other types of stars. So these are called pulsars or quasars. So these are blue. These are neutron stars. Oh no, not neutron. That's not the word I'm looking for. Shh, erase that. Shh, erase that. Shh. These are, but that color. Young stars that shoot out beams of energy and radio waves. So what's happening, why they call it a pulsar is because they're pulsing. It's a, where, Quinn? In here? It's a U. It is a U, buddy. So what's happening with these is there you've got a star, and coming out of either end of it are these beams of superheated energy and radio waves. And so how we're able to know this happens, because scientists were starting to we've got big satellites that are pointed at the universe, and they kept picking up these really riveting. It would go bing, and then nothing. And then bing, and then nothing. And then bing, and then nothing. And they're like, what the heck is this? So then they looked with the big telescopes, and then they saw these lights also going boop, boop. And they figured out that they're these giant, super-powered stars. So like the other ones are like a car. This is like a car with a bunch of nitrous poured in to make it go faster. They're superheated, and they're shooting stuff out all the time, and they're spinning. Kind of. Much worse than a hurricane. So we're actually able to use these to be able to tell distances. We can use them for telling where things are, because we're like, okay, that's this pulsar, that's this pulsar, that's this pulsar. So, next up, black holes. These are collapsed stars. That's grammar is terrible. That are so dense. Now, who knows what I mean when I say dense? Hands up if you've heard somebody talk about density before. Do you know what it means?
It means
No.
how heavy something is.
Not quite how heavy it is.
And how much stuff it has in it.
It's like if there was a box and I put 5 cotton balls in it and it filled it up, it wouldn't be very dense, but it would still be full. But if I took a box and I filled it with 1,000,000 grains of sand, that would be a very dense box because everything is really tightly packed together. So a black hole is what happens when it goes nova, sucks everything together, and like the whole of that enormous, many million kilometers wide star is sucked into a space like this big. And what happens when that happens is on this right here. So imagine space. We'll do this as an experiment. I need to buy a sheet of fabric, and we'll do this as an experiment. Imagine space is this flat plane. And the bigger something is, the bigger a dent it makes. So a normal star, so this is like the sun. The sun makes a little dent in space because it's so heavy. This is a neutron star. So it's got a little bit more stuff. It makes a little heavier dent in space. This is what happens with a black hole.
Yikes.
It's so heavy that it makes this like ginormous hole. Not even a hole. We don't even know whether it's a hole. We don't know whether it comes out the other side. But it makes this space in space.
Depends what stands to the sheet
We don't know. No one knows whether it goes to another place. Because again, everything basically once you get to, we'll do this in. I should stop now because otherwise I'll go into a whole thing about black holes. I'll stop now. Another lecture on black holes. Black holes need their own lecture all on their own. Okay?
Do you promise that?
Yes. Promise. What's up? No, it's okay. We'll go till 2. Everybody good on black holes and other types of star?
Yeah.
Okay. We'll get one. Skip those 2. We're gonna go to nebulas. Nebulas are cool. That's a nebula. So these are also called star nurseries.
Aw, that sounds so sweet. Only
Because this is where stars are born.
there you go.
Kieran, focus up.
So the boy bear just launched into the universe.
So a star Kieran, focus up. You're not. You're talking to Joseph.
I can hear you fine.
Great. So what a nebula is basically, it's a bunch of gases that never got squished into a star. So they're just kind of out there floating around in space. A bunch of hydrogen and helium and nitrogen all floating around out there, doing their own thing. And they're just not hot enough to start that fusion reaction to make a star out of it. But sometimes it'll happen and a star kind of like will float out, or a bunch of will come together and the star will suck in the nebula. But yeah,
What?
they're really, yeah.
Huh.
Like once it starts, then everything gets sucked into it, and the nebula could disappear.
So there's like a million nebulas.
There's, I cannot even begin to tell you how many nebulas there are.
All nebulas.
Millions and millions.
So many. I cannot put a number on it.
What if all nebulas disappear?
That would be bad.
Very.
That would be bad.
What will happen?